What is statistical learning? Suppose that we are statistical consultants hired by our client to provide advice on how to improve sales of a particular product. The advertising data set consists of the sale of that product in 200 different markets, along with advertising budgets for the products in each of those markets for three different media: TV, radio, and newspaper. The data are displayed in Figure 2.1. It is not possible for our client to directly increase sales of the products. On the other hand, they can control the advertising expenditure in each of the three media. Therefore, if we determine that there is an association between advertising and sales, then we can induce our client to adjust advertising budgets, thereby indirectly increasing sales. In other words, our goal to develop an accurate model that can be used to predict sales on the basis of the three media budgets. In this setting, the advertising budgets are input variable, while sales is an output variable. The input go by different names such as predictors, independent variables, feature, or sometimes just variables. The output variable, in this case sales, is often called the response or dependent variables. You can see in Figure 2.1 the advertising dataset. The plot displays sales in thousands of units as a function of TV, radio, and newspaper purchase in thousands of dollars for 200 different markets. In its plot, we show the symbolic square fit of sales to that variable as described in Chapter 3. In other words, its blue pie represents a symbol model that can be used to predict sales using television, radio, and newspaper, respectively. More generally, suppose that we observe a quantitative response Y and B different predictors is 1 is 2 etc. to SP. We assume that there is some relationship between Y and X, which can be written in the very general form. You can see here f is some fixed thus unknown function of x1 to xp, and r is a random error term which is independent of x and has mean 0. In this formulation, f represents the systematic information that is provided about y. As another example, consider the left-hand panel of Figure 2.2, a plot of income various years of education for 30 individuals in the income dataset. The plot suggests that one might be able to predict income using years of education. However, the functions f that connects the input variable to the output variables is in general unknown. In this situation, one must estimate f beyond the observer points. Size income is a simulated dataset. X is now and is shown by the blue curves in the right-hand panel of Figure 2.2. The vertical lines represent the error terms. We note that some of the 30 observations lie above the blue curve and some lie below it. Overall, the errors have approximately mean zero. Figure 2.2. The income datasets in the left. The red dots are the observed values of income in tens of thousands of dollars and years of education for 30 individuals. In the right, the blue curve represents the true underlying relationship between income and year of education, which is generally unknown. But is known in this case because the data were simulated. The black lines represent the errors associated with each observation. Note that some errors are positive. If an observation lies above the blue curves and some are negative if an observation lies below the curves. Overall, the errors have approximately mean zeros. In general, the function f may involve more than one input variable. In Figure 2.3, we plot income as a function of year of education and seniority. Here f is two-dimensional space that must be estimated based on the observed data. Figure 2.3. The plot displays income as a function of year of education and seniority in the income dataset. The blue surface represents the true underlying relationship between income and year of education and seniority, which is now seen the data are simulated. The red dots indicate the observed value of the quantities for 30 individuals. In essence, statistical learning refers to a set of approaches for estimating F. In this chapter, we outline some of the key theoretical concepts that arise in estimating F, as well as tools for evaluating the estimate obtained. Why estimate F? The first one is prediction. In many situations, a set of inputs is readily available for the output which cannot be easily obtained. In this setting, since the error term averages to zero, we can predict by using the the formula like we can see on the slide, where f represents our estimate for f and y represent the result prediction for y. In this setting, f is often treated as a black box. In a sense, task 1 is not typically concerned with the exact form of S. Rather, it yields accurate prediction for Y. Another example, suppose task is 1 to its P or characteristics of a patient blood sample. that can be easily measured in lab. And once a variable encoding the patient risk for a certain adverse reaction to a particular drug, it's natural to seek the best way using it, since we can then avoid giving the drug in question to patients who are at high risk of an adverse reaction. That is, patients for whom who estimate of Y is high. The accuracy of Y at a prediction of Y depends on two quantities, which we will call the reducible error and the irreducible errors. In general, F will not be a perfect estimate for F, and this inaccuracy will introduce some errors. This error is reducible because we can potentially improve the accuracy of S by using most appropriate statistical learning techniques to estimate F. However, even if it were possible to form a perfect estimate for F so that our estimate responds to the form y equal F is, our prediction would still have some errors in it. This is because y is also a function of uh, R, which by definition cannot be predicted using it. Therefore, variability associated with R also affects the accuracy of our prediction. This is known as irreducible errors, because no matter how well we estimate F, we cannot reduce the errors introduced by R. Why is irreducible error lesser than zeros? The quantity may contain unmeasured variables that are useful in predicting Y. Since we don't measure them, F cannot use them for its prediction. The quantity may also contain unmeasurable variation. For example, the risk of an adverse reaction might vary for a given patient on a given day, depending on manufacturing variation in the drug itself or the patient's general feeling or well-being on that day. Consider a given estimate F and set of predictor it without the prediction y equal F is assume for a moment that broad F and is appears, then it's easy to solve that. Where represent the average or expected value of the square difference between the predicted and actual value of y, and bar represent the variance associated with the error term R. The focus of this book is on techniques of estimates with an aim of minimizing the reducible errors. It is important to keep in mind that the irreducible error will always rely on upper power on the accuracy of our prediction for y. This bar is almost always unknown in practice. The second purpose of estimate is inference. We are often interested in understanding the way that y is affected at the x1 to xp change. In this situation, we wish to estimate f, but our goal is not necessarily to make rep prediction for y. We instead want to understand the relationship between y and d, or more specifically, to understand how y changes as a function of x1 to xp. Now it cannot be tested at black box because we need to know its exact form. In this setting, one might be interested in answering the following questions. Which predators are associated with the response? Is it often the case that only a small fraction of the available predators are substantially associated with Y? Identifying the few important predators among a larger set of possible variables can be extremely useful depending on the application. What is the relationship between the response and its predator? Some predators may have a positive relationship with Y in the sense that increasing the predator is associated with increased value of Y. Other predators may have opposite relationships depending on the complexity of F. The relationship between the response and a given predator may also depend on the value of the other registers. Can the relationship between Y and its predator be adequately summarized using a linear equation, or is either relationship more complicated? Historically, most methods for estimating F have taken a linear form. In some situations, such as assumption is reasonable or even desirable, but often the true relationship is more complicated, in which case a linear model may not provide an accurate representation of the relationship between the input and output variables. For instance, consider a company that is interested in conducting a direct marketing campaign. The goal is to identify individuals who will respond positively to a mailing based on observation of demographic variables measured of each individual. In this case, the demographic variables serve as predictors and respond to the marketing campaign, either positive or negative, serve as the outcome. The company is not interested in obtaining a deep understanding of the relationship between its individual predator and the response. Instead, the company simply wants to accurately model to predict the response using the predators. This is example of modeling for predator prediction. In contrast, consider the advertising data illustrated in Figure 2.1. One may be interested in answer questions such as which media contribute to sales, which media generate the biggest boost in sales, or how much increase in sales is associated with a given increase in TV advertising. This situation falls into the inference paradigm. Another example involves modeling the brand of a product that a customer might purchase based on the variables such as price, store location, discount level, competition price, and so forth. In this situation, one might really be most interested in how each of the individual variables affect the probability of purchase. For instance, what effects will changing the price of products have on sales? This is an example of modeling for inference. Finally, some modeling could be conducted both for prediction and inference. For example, in a real estate setting, one may seek for relative value of homes to input such as Climate zoning is done from a river air quality, school income level of community, size of policy, and so forth. In this case, one might be interested in how the individual input variables affect the price. Thus, how much extra we view a house be worth if it had a view of the river. This is an inference problem. Alternatively, one might simply be interested in predicting the value of home given its characteristics. It is how under or overvalued. This is a prediction problem. Depending on whether our ultimate goal is prediction, inference, or a combination of the two, different methods for estimating F might be appropriate. For example, linear models allow for relatively simple and interlinear model interpretable inference, but may not yield as accurate prediction as some other approaches. In contrast, some of the highly nonlinear approaches that we discuss in the later chapter of this book can potentially provide wide accurate prediction for Y, but it comes at the expense of less interpretable models for which inference is more challenging.